Good evening, friends. I am Shivan Gowda Biradar. So I am a PMRF PhD fellow in Control and Automation Department at Department of Electrical Engineering, IIT Delhi. So basically, this is week 5th, and today we'll be looking at let me adjust my pen actually. So yeah, today we'll be looking at two very important topics that are transformations. Basically linear transformations, a very important word here. And then we'll look into some important questions on four fundamental subspaces. Four fundamental subspaces. So today we'll be basically covering these two topics. I hope you are enjoying the assignments, those 10 questions which I am posting. Yeah, so let us move on to week 5th assignment. Yeah, so the first question says that consider a vector space V of dimension 47, and inside this, so we have a vector space V, right? And inside this vector space V, we have two subspaces W1 and a subspace W2. It is said in question, it is given in question that the dimension of W1 and dimension of W2 is already given to us. So the dimension of W1 is given as 22 and dimension of W2 is given as 26. So obviously it will be something like this, right? So the question is, what is the maximum possible dimension of W1 plus W2? So this is a very easy question, and this can be answered in two ways here. So I'll start with a very simple reasoning. So remember that dimension of W1 plus W2 is equal to dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2, right? So, and there is no doubt that this result is true. Okay. So from this result, I can directly say that the dimension of W1 plus W2 is less than or equal to 47. Since the dimension of V is already given to us, there is no doubt that the dimension of W1 plus W2 must be less than or equal to 47. So, or equal to 47. So this is one reasoning because because W1 and W2 are the subspaces of the vector space V. So obviously the dimension of W1 is always lesser than vector space V, and the dimension of W2 is always lesser than vector space V. So the dimension of W1 is always less than vector space V, and the dimension of W2 is always less than vector space V. Even though if I add these dimension of W1, dimension of addition of these two subspaces, if I add these two subspaces, I would get another space. Then also the dimension of these two spaces must be less than or equal to vector space V. So these relations hold. So there is no doubt that dimension of W1 plus W2 is less than or equal to 47. So this is an upper bound. So this is one reasoning, one very easy reasoning, direct reasoning. Let us go on to other reasoning. So in the question, it is given the dimension of V is 47. W1 and W2 are two subspaces, right? Okay. So dimension of W1 is 22, which is given to us. Dimension of W2 is 26, which is again given to us. So if W1 is a W1 direct sum W2 is equal to vector space V, then dimension of W1 plus W2 would be dimension of W1 plus dimension of W2. In this case, if this is a direct sum, W1 intersection W2 would be your nulls. Right. So the dimension, this implies that dimension of W1 intersection W2 is equal to 0. So the dimension of W1 plus W2 is equal to 47 if and only if this is true. So at this point in time, seeing these two dimension, I don't think I don't think this is true. So, but for our convenience or for our knowledge, I have given this. I have explained this to you. So we know that dimension of W1 plus W2 is equal to dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. Again, if W1 direction W2 equal to V, then this would be 0. But seeing, observing these two numbers, I don't think this is true. So this is not equal, this term in our case is not equal to 0. So we know the dimension of W1 is 22, dimension of W2 is 26. So we get this expression. Okay, so this case is impossible at present because of the given data. If dimension of W1 intersection W2 is 1, then we get the dimension of W1 plus W2 as 47. So let us say that dimension of W1 intersection W2 is equal to k, which is greater than 1. So again, we get this thing. So again, the dimension of W1 plus W2 is upper bounded by 47. So the answer would be that this is the answer. Okay, this is a very easy question. So let us move on to the second question. There exists a linear transformation T from R square in R to R square in rational numbers, such that T of the vector 1 0 is equal to again the same vector 1 0, and the T of 0 1 is again the vector 0 1. This seems like this is an identity transformation. So is this true? So look at this carefully. Here it's Q and here it's R. This observation is itself saying us that this is false. So let us move on to our third question. So we have a linear transformation T, which is in R square to R square. Which of the following cases T square is an identity transformation? So let us first start with this thing. Let us say that our linear transformation T is a reflection about x-axis. So we have this case now. We are looking into this case. We have to see whether, okay, so let us look into this case. We have an initial vector xy. The reflection of this initial vector xy would be minus x, y. So we must design a transformation T such that this is true. So this is possible only when your T is like this. So if this is true, so your T basically for a reflection is like this. So if you take a composition of this T two times, T composition T, then I'll get an identity. So which means that T composition T, which is also written as T square, is equal to I. So so the so T is a reflection of about x-axis. Then if I take T square of this transformation, then I'll get I. So this is one case. This is one case which is satisfying this property. So let us look into the projection of this. So let us say that we have this initial vector xy. If I take a projection of this vector, then I'll get x comma 0. So which means that I have to design a transformation T, which when multiplied with this vector xy will give us the vector x0. And this is only possible with this matrix, this T. So, but if you take a composition of T, which is T square, this is not equal to I. Right. So this is not your answer. Again, the same thing would be with this. So the fourth question is, let us consider a linear transformation T from U to V. And S is any subset, remember this is a subset of U, then which of the following is true? This is actually a very important question here. So If S is linearly independent, does this imply T of S is linearly independent? If T of S is linearly independent, does this imply S is linearly independent, or both A and B are true? Let us see that. So we'll start with this argument and see whether this is true or not. So we have from our question that T is a linear transformation from U to V. S is any subset of U. So let us look into our first argument. Yeah. So this is my first argument. Okay. So if S is linearly independent, so my first argument says that if S is linearly independent, then T of S is also linearly independent. We have to check whether this is true or not. So S is linearly independent. So let us assume that S is linearly independent, right? So this means that this is true for all alpha I is equal to 0 when I equal to 1 to R only. So I'll take a linear transformation on both sides. I'll multiply T here, I'll multiply T here and a T here. So what I see is that since T is a linear transformation, I can directly multiply T with these vectors U1 to UR. So I'll get this expression. So this is T of 0. This is T of UR. This is T of U2. This is T of U1. So I can arrange this whole expression as a system of linear equations. And this is, so I can write this matrix as A, this unknown matrix as alpha, and this is 0. Right. So now alpha might be anything, right? Alpha obviously is a trivial solution. The trivial solution, this trivial solution obviously would satisfy this. But alpha could also have other values. Alpha could also have other values. So this does not guarantee. So this is not right basically. So if S is linearly independent, that does not guarantee that T of S is also linearly independent. Now let us look into the second argument. This is our second argument. Okay. So second argument says that if T of S is linearly independent, then S is linearly independent. So let S be defined as this. So S is a subset of vector space U and is given as this set, which containing U1 to UR. Vectors U1 to UR. And T of S is a transformation of each of the individual vectors TU1 to TUR. So it is said in question that T of S is linearly independent, which means that this is true. So since T is a linear transformation, I can write this whole expression in this way, right? And so this, right? Okay, let us let us not go into this. So at present, I have this expression. Okay. So since T is linearly independent, T is linearly independent, this implies that T is full rank. T is full rank and T inverse exists. Right. So this is true. And since T is full rank, T inverse is also full rank. T inverse of 0 is equal to 0. No doubt about it. And this is for all alpha is equal to 0. So this implies that if T of S is linearly independent, then this set S is also linearly independent. So yeah, let us move on to our fifth question. So in fifth question, we are being given a coordinate vector here. A coordinate vector is alpha, beta, and gamma, and this coordinate vector is corresponding to the vector 1 to 1 in R3 and relative to the ordered basis this. So this basically means this. So this is your vector and this is your basis. So this vector x can be expressed in terms of these three vectors. So this is given as this, and these are your coordinate vectors. And these three numbers belonging to real number r forms your coordinate vector alpha, beta, gamma. Okay. So this equation can be written as a system of linear equations, ax equal to b, and from this you can get the values of alpha, beta, and gamma. So as per our question, they have asked what alpha is. So alpha is equal to 0.5. So let us move on to sixth question. So let us consider a linear transformation T, which is given as a transformation from R2 space to a transformation from R2 space to R4 space, and this is given by this. Okay, so we have to find out what T is actually. So the T when operates the T when operates on this vector gives us this vector. T when operates on this vector gives us this vector. So they have asked an indirect question as to what expression would we get after finding T. Right. So basically we have to find T first, then we have to multiply this T with x1, x2 and see how this x1, x2 are related to our unknown variables or unknown variables y2 to y1 to y4. So let us start with finding T, then multiply this T with this vector to see how this x1, x2 and these four variables are related to each other. So it is given. So this is given to us. This is given to us. This is given to us. By observation, it is seen that T must belong to 4, 2. T is a matrix, a non-square matrix with 4 rows and 2 columns. Let us say that. Let us say that T is this thing, this non-square matrix, and we'll use this expression now. T when multiplied with 1, 1 will give us a vector of ones. Will give us a vector of ones. Okay. So we multiply these matrix with 1 to give us 1. So, and we'll use another condition. Again, this condition where T is assumed to be this matrix when multiplied with 1 and -1 would give us all of -1 vectors. So this is what we get. So when we gather all the equations, we'll use these two equations. We gather all these equations first, and then we'll use an individual pair of equations. Okay, we'll use these equations to find a1, a2. We'll use these two equations to find b1, b2. We'll use these two equations to find c1, c2, and then we'll use these two equations to find d1 and d2. So what we see is that we'll get these sets of knowns. So a1, b1, c1, and d1 are 0. a2, b2, c2, and d2 are 1. So our transformation matrix T is basically this. So now let us multiply x1, x2 with this transformation matrix and see how this vector and this vector are related. So what we get is that this thing, right? So this is how the x1, x2, this vector and this vector are related. This vector and this vector are related. So x2 is equal to y1, x2 is equal to y2, x2 is equal to y3, and x2 is equal to y4. So this finishes our fourth question. So in our seventh question says that there exists a unique linear transformation T from R square to R square, which maps all the vectors on the line x plus y equal to 0 onto themselves. Okay. So what we have here is that we have a line y equal to minus x or x plus y equal to 0, and we have to see whether there exists a transformation T which when multiplied with a vector on this line which when multiplied with a vector on this line, again projects a transformed vector is again on this line. So if I take a vector on this line, multiply this with t, then I'll get a vector, a transformed vector which is again on this line. So I have to find that type of transformation. I have to see whether that transformation exists or not. So let us first write the equation of line in a vector form. So we know that y is equal to minus x. So this can also be written as x, y is equal to alpha minus 1, 1. And alpha belongs to real number. Okay. So remember this equation represent this whole line, represent this whole subspace or this whole line. So now the question is, does there exist a transformation T which when multiplied with this value or which when multiplied with this value brings in another vector on the same line? So this is our equation which represents the line y equal to minus x. And when we apply a transformation T on this vector which is on line y equal to minus x, I must get back a vector beta into minus 1 1. Okay. So does there exist such transformation? So this such transformation is only possible when T is equal to T is a diagonal matrix or is an identity matrix. Okay. So the vector on y equal to, so this vector which is obviously on y equal to minus x, line are transformed back to line y equal to minus x. So only when this is possible only when T is an identity matrix. Okay. Other than this, there are no linear transformation which can do this. So T must be an identity diagonal matrix with the same elements on the diagonal, principal diagonal elements. In which of the following case? So the eighth question is: in which of the following case there exists a linear transformation T from R square to R? Again, we have to check whether there exists a linear transformation T which does this transformation, and this transformation. I have to see. The question says that I have to find a linear transformation T which does this transformation and does this transformation. Again, this is a simple. We'll get a simple system of linear equations, solve this, and see whether this is possible or not. So we'll check our first argument, which says that transformation of 1 2 must give us 3 0. Again, the same transformation T when applied on 2 1 must give us 1 and 2. So let us assume that T is of this form, and if T is this of this form, we'll use this result here, and we'll use this result here. Now our aim would be to find A1 A2 B1 B2. Okay, so we'll solve this to get this equation. We'll solve this to get this equation. So again, we'll use individual pair of equations to find A1 and A2 and individual pair of equations to find B1 and B2. So from which we can directly calculate both A1 and A2, A1, A2 and B1, B2. So we'll get this type of transformation, which means that there exists a transformation, which does this transformation. And again, if you follow the procedure, you will get that there exists a transformation T which does this work. Okay. And these are fairly simple questions actually. So now let us jump on to our ninth question. This is an important question, and this is where you will get to know the important concepts of 4 fundamental subspaces. Okay. So let us consider a linear transformation T from R square to R square such that T square is equal to T, and we have two subspaces W1 and W2. Okay, and W1 is defined as set of all W1 is defined as T of x for all x belonging to R square. So this is basically a range space of transformation T, and W2 is set of all x such that Tx equal to 0. So this is basically null space of transformation T. So we have to check which of this is true. So Till now we have this information which says that T is a linear transformation from R square to R square, and T square is equal to T. And we have subspaces W1 and W2 which are defined as this. So obviously both of these are subspace. This means that 0 belongs to W1 and 0 vector belongs to W1, 0 vector belongs to W2. This also means that W1 plus W2, 0 belongs to W1 plus W2. And remember that W1 is a range space of the linear transformation T, and W2 is the null space of the linear transformation T. So if X belongs to W2, then Tx equal to 0 belongs to W1. And the inner product, so the inner product of X, this vector, and inner product of Tx is obviously equal to 0. So this implies that the range space of transformation is perpendicular to the null space of the transformation. If this is true, then this is true. This is a very important result. Okay. So W1 plus W2 implies that W1 direct sum W2 is equal to R square. So I hope this makes this clear. So now let us move on to the last question. So we have a vector space V, and corresponding to this vector space we have three subspaces W1, W2, and W3. And it is given to us that V, the vector space V, is the direct sum of W1 and W2, and the vector space V is the direct sum of W1 and W2, W3. So now the question is whether W2 is equal to W3. This is a very interesting problem actually. So going the way through the dimension formula, it seems that the subspaces are same, but there is a little bit of observation needed here. So let us assume that the dimension of the vector space V is n, and it is given to us that dimension of V is the direct sum of W1 and W2, which implies that this is true. Right. This means that if this is true, then dimension of V is equal to dimension of W1 plus W2, since W1 intersection W2 is equal to a null set, which implies that dimension of W1 intersection W2 is equal to 0. So this is true for this expression. And it is also given to us in question that V is the direct sum of W1 and W3, which implies that this expression is true. From these two expressions, we get the dimension of W2 is equal to dimension of W3. But the question still remains whether W2, the subspace W2 equal to W3. Let us graphically solve this actually. That will be more intuitive and more understandable. So let us take a R2 space, and let us take three subspaces in this R2 space. Let us take this subspace W1. This should be one subspace, and let us take another subspace W2. And we have another subspace W3. Okay. So W1, the direct sum of W1 and W2 would give us R square. And again, the direct sum of W1 and W3 will give us R2. But are W2 and W3 equal here? Obviously, they are not. So this implies that the answer is false. This implies that W2 is not equal to W3. So the week 5th assignment was a very fairly simple assignment. So I think we have solved 10 questions here, and I think uh, today's lecture would be over here. Thank you. Have a nice day.